start of the second day of the workshop. It's a pleasure, of course, to welcome one of our own, Ronnie Nagloo, who's going to talk about strong liminality and the Fuchsian triangle. And there is, by the way, coffee and breakfast wherever.
Thank you. Thanks for the organizers for giving me the opportunity to speak today. So after yesterday's talk, I somehow decided I would change a little bit what I was planning to say. Say a little bit in the spirit of what we've seen about. So here I will look at the family of differential equations, and somehow we'll ask the question of whether they're strongly minimal. And part of the talk will be to explain why this family in particular is interesting. So let me quickly start with notation, conventions, and a few things. So U will be a universal differential equals field, so saturated from all theories, and I'll take the complex number, field of complex number to be constants of U. Right. So the S will denote quadrant derivative, whereas the A will be the automorphic derivative. I'll say a little bit more about them as we go along. And so finally, so RV1, V2, V3 will be the rational function given here, so you don't have to remember what they are, but V1, V2, V3 are complex numbers. All right? And so the question I'm interested here is, for which triple of complex numbers are the differential algebraic variety given by the automorphic derivation and that rational function strongly minimal? All right? And so, so we've seen several ways to define strong minimality yesterday. So here's one more way in this particular case. So strongly minimal, remember, is for any differential field extension of C and any solution, you only have transcendence degree 0 or 3. So remember that the Schwarzian is a third order derivation. Yes?
Could you go back to the previous slide?
Yeah.
It seems like your
Third
R, V1, V2, V3 only depends on this Hauptmoduls.
So exactly. So part of the talk will be to somehow go through why first this equation and why this form and why it's interesting. Right? Good. And so, as we'll see as we go along, for some V1, V2, when they are rational, so when they are the reciprocal of natural numbers, they are somehow very interesting. They have very interesting arithmetic questions around there. And for others, it's, as we look like for generic V1, V2, V3, that'd be sort of more theoretic curiosity to know whether for generic parameters, yes.
Yeah, I have a question. Will you ever let one of the VI's be infinite, the point at infinity?
So the idea is no, right? But we shall see in a minute as we go along that it's somehow related, right? And so now, so let me introduce triangle groups. All right. So given three integers or infinity, m1, m2, and 3, such that the sum of reciprocal is less than 1. All right? And so that's, I guess, why James was asking whether I let it be infinity. So later on, the V1, V2 would be 1 over each of these. All right? So a triangle group, so if we look at an hyperbolic triangle with angles given by pi over these integers, then the hyperbolic reflection of the side opposite to an angle. So let's call this V1, and that's the hyperbolic line. So the hyperbolic reflection is leaving the geodesic fixed and somehow reflecting the other angles. All right, and so a triangle group is a subgroup of SL2R whose image is generated by this reflection given. Now, this is somehow not a lot of information, but as an abstract group, so you have generated by the image of in PSL2Z satisfying, so let's denote that the image, so the identity, and here comes the and so generated by elements that satisfy the following relation, and when m, one of the mi's is infinity, you ignore the last line. Right, so this is a triangle group, but somehow for those who are familiar with signature of the Fuchsian group, so a triangle group of type M1, M2, M3 is one of a Fuchsian group of first kind with signature 0, M1, M2, M3, right?
Can I ask you a question?
Yes.
Can we go to the previous slide?
Yeah.
So the points of V1, V2, V3, are those points in the upper half plane there? And then your arcs are semicircles? I mean, in the picture.
Yeah, so in the picture you're hyperbolic, so you're thinking of the hyperbolic.
Yeah.
Right, and so you're taking, all right, so here's something not to, so the V1, V2, V3 here aren't the V1, V2, V3 we looked at, right?
Oh, so, that's what I meant.
Yeah, exactly, sorry about that,
Yeah.
these should be W's. Or something. These are vertices, points on.
Can I ask another question?
Yeah.
How it's not a fair question, but how are the W's related to the previous B's exactly in some simple formula?
I don't think so, no. Okay. So somehow the VI's would be, so I'll say that again, so the VI's will be 1 over, so called the angular parameters. Right?
Oh.
So they're simply the angular parameters. So they give you the angles of the hyperbolic triangle. All right, so I won't say much about what Fuchsian group, the signature of a Fuchsian group, but I'll focus on the 0 here, and that will be somehow enough for us. So we can somehow look at linear fractional transformation. If I give you a triangle group, so the usual one, so the action all right, and so one can ask the quotient of the upper half plane with these triangle groups. And so it's always, the compactification is always of genus 0. So that's what the 0 in the signature here means. Yes?
Is it reasonable and correct to think of this triangle group acting on the upper half plane by those compositions of reflections in those?
Yeah, absolutely. Yeah. So that's precisely the picture you have to have in mind. Tessellation.
So the inside of that thing you drew is like the fundamental domain.
Yeah. So you have to do one reflection and you get the fundamental. Exactly. And so, yeah, so the genus 0 is because the compactification of quotient is genus 0 Riemann surface. But just note that if infinity doesn't appear, so if you're a type finite type, then already the quotient is compact. So you call this triangle group compact. But if you have infinity appearing, so there's cups, the quotient, this quotient is not already compact, so that's why you have to look for the compactification. So you add to the above planes cups. Basically. All right, so this is terminology. So whenever the mi's are finite, we call them compact. When at least one is infinite, we call them non-compact triangle. All right, so here we go. So here I call them nu to differentiate them from V, because we are not yet looking at the differential equations. But so we call the angular parameters are the reciprocal of these, and let's fix a triangle group of type M1, M2, and 3. So now the quotient or the compactification is of genus 0. So the function field is generated by a single function. Let's call one of them J nu, and this is called the Hauptmodulus or Hauptmodule for the group, and it's defined up to linear fractional transformation. Yes.
This curly x sub gamma y is the quotient of.
So that's the compactification of. So for when it's not compact, you have to add gaps. All right, and so turns out that you can extend such J to a meromorphic function on H, and this becomes an automorphic function with respect to gamma nu. So automorphic means if you take any G in gamma nu, then it's invariant under the action linear fractional transformation. So also the function field is isomorphic to the field of automorphic function with respect to gamma nu. So any over automorphic function is a rational function of one of the modules. All right? And so now let's say a few words about the derivative I sort of mentioned earlier. So both the Schwarzian derivative and the automorphic derivative aren't really derivative, but they satisfy a well-known composition rule. So S, ds of f composed with G is ds of f times G prime square plus ds of G. So, and by somehow dividing by G prime, you get a composition rule for the automorphic derivation as well. And so why one is interested in by the name of it, is if you start with an automorphic function with respect to some triangular group, or generally a Fuchsian group, then the automorphic derivation applied to that function, the function you get is also automorphic. All right? And so this is somehow the idea behind, if we somehow apply the automorphic derivation to J of V, one of the module, we get another automorphic function. And so this automorphic function is a rational function of J of U. And it turns out there's some work to do, but the automorphic function is precisely this rational function we had before.
I have another question. So this is in the genus 0 case.
In the genus 0.
Yeah, and so is it easy to work out? I mean, in the non-genus 0 case, I guess you just get an algebraic relation involving dA of JB, right?
Yeah.
But is it easy to work out what that algebraic relation is, like computationally, or is it?
So I'm not quite sure. Because I've only looked at genus 0. Or it's not too easy to somehow.
It's already hard enough.
Yeah, exactly. Yes.
And just sort of a background history question. Obviously, Schwarzenegger relative Fuchsian groups and things like that are relatively ancient history. But what about these equations, these particular equations?
So somehow they, in some cases, they've been looked at. For example, the work of Jim and Tom is not exactly the same equation, but up to change of variables, you do get these. So there are cases that have been looked at, but not in full generality.
I guess what I was really asking is not whether other models there are certainly with it, but whether people who care about differential equations and thought about strong minimality have ever thought about these equations.
There are some works, yes, there are some works around, and indeed there's a lot more what can be said, but I mean,
I was curious.
but yes, there are some people have looked at it. And so for us, any Hauptmodul is a solution to the differential equation with the parameters given by the angular parameters. All right. And so more is true is if you somehow take any G, any element of GLNC, and you compose with an Hauptmodul, then using somehow the composition rule there, it's not too difficult to show that this is what they are also solutions of the equation.
How do you compose something in GeoMC?
Pre-composition.
Yeah.
So this is a function from where to where?
So J is H. Remember, so
With J to H31.
Upper half.
upper half plane, right? So you can extend.
So GLN is not the upper half.
No, so but it acts, right? The action.
What is
So,
it?
He means geo.
You mean GL2?
two, yeah, not two. Oh, is that an N?
Yeah.
Oh, I'm sorry. Oh yeah, there's a two there. It's supposed to be a two.
No,
Yeah,
no
that's-
N.
That's the way I can make that. All right, and so some now some terminology, and so this is to go back to what Alex was saying. So for now, back to our differential equation, for the V's where correspond to a Fuchsian triangle group, the functions of the Hauptmodul are sometimes called the triangle functions. And so other people who look at this equation call those that aren't from a Fuchsian type Schwartz triangle function. And that's because I think Schwartz was the one who somehow first looked at this equation in this generality.
Wait, what does it mean exactly to not be a triangle group that's
Oh, so-
non-Fuchsian?
Remember, so the V's here have to be so 1 over, so
Oh, I see.
1 over and have to add less to
Yeah.
1, right? The sum should be less than 1.
But that doesn't happen, then you somehow you won't be like
Hauptmodul.
dense or something.
No, so no, yeah, but still somehow these functions are because you can obtain them.
Okay.
So they still look at them, and, right? And so, so I was just saying for generic parameters, we really would be looking at Schwartz function and trying to understand if these equations are strongly minimal in that way. But for triangle functions, we can somehow split the problem in two. So there's the notion of arithmetic or non-arithmetic triangle group. So now, so this is not a perfect definition, and indeed it's not. It's just an equivalent way to explain what arithmetic is. So recall that two groups or two triangle groups are commensurable if their intersection has finite index in the both of them. All right, and a result of modulus is that a triangle group is arithmetic if and only if the commensurator is dense in PSLR, where the commensurator is what you expect. All right, and so what's the point behind commensurator is, first of all, if it's your non-arithmetic group, then your commensurator is a triangle group, and indeed the largest subgroup, largest group containing the group. But somehow, for those who know a little bit about modular functions and decay operators, if you have dense commensurator group, then you have enough decay operators, and that yields interesting arithmetic properties. For example, when you look for the Q series expansion or Fourier expansion of the Hauptmoduls.
Can I ask you a question?
Yes.
Is it true that there is only, is something like this true? There's only finitely many commensurator classes of arithmetic groups, right?
So so the next result will tell you all they are. You probably know that there's 85 of them, but but somehow I think that's an open question to put them in the commensurate class. Right. So anyway, so first part of James' question is a result of Tassuichi is you have a full classification of the arithmetic triangle. So there's, I think, 76 of the compact case, those, and there are 9 of the non-compact case, right? And so note that here there are, these are very interesting cases, and proving strong minimality there is perhaps James as well is trying to do something like that. But somehow I'll focus on the non-compact case today. So now what are the results that there are there? Then there's, to start with, James and Tom result, which says that when the triple is 2, 3, infinity, then the DAV is strongly minimal, and even more so geometrically trivial, non-omega categorical. Now, they didn't look, as I said before, they didn't look at this particular form of the equation, but the idea is the group, the triangle group is the same, and so the Hauptmoduls are automatically related, interdefinable. And so, perhaps, just to mention how they not how they prove it, but ingredients, because we'll need them. So first there's Nishioka's result that states that triangle functions do not satisfy AD of order 2, all right? So it's a lot more than that. It's for all many Fuchsian group. So triangle functions do not satisfy any OD of order 2 over C. And another ingredient, which is the Ax-Lindemann-Weierstrass derivative, and this states that if G1 to Gn do not lie in the same coset of GL to Q, then let me back to the here. So the tuple are algebraically independent. All right. So when u is taken to be 2, 3, infinity. All right. And so that's Jonathan result. And so that very nice result of Jim and Tom to cleverly use the interaction. And of course, they prove a lot more in that paper. But somehow, they also explain that any arithmetic subgroup of SL2C is strongly minimal, geometrically trivial, non-categorical. All right, and so out of the 9 non-compact, these correspond to infinity, infinity, 3 infinity, and infinity, and these are the group gamma note 2. So let me perhaps say. So gamma node n is so if you look at the classification, it's somehow well known that you can realize these triangle groups as the congruent subgroup of level 2, 3, and 4. And the proof of this, or the argument they say is not too difficult, is you know that any of, let's call it G2, G3, G4, so are algebraically or interalgebraic with G, let's call that one G0. Should be G1, that's fine. All right, so now G0, the type is strongly minimal, and so they are interalgebraic, so the types are strongly minimal, and then, I just erased Nishokas. And using Nishokas, you can just somehow conclude that you have that even for these one, the equations are strongly minimal. Now, so these are 4 out of the 9 non-compact triangle group. So the others aren't a subgroup of SL to Z. All right, so, and one may wonder whether the same is true, whether you can somehow find interalgebraicities, yes?
I have a question.
Yeah.
So for arithmetic here, you mean that the commensurator is SL2 of Q? That's right. That's what this definition of arithmetic, right? I mean, that's how. Is that right? I mean,
No.
But I thought.
So in this case, it will be, right?
Yeah, that's what I mean. But I'm saying that argument there doesn't the argument doesn't the argument that's going on there, the interalgebraicity argument, depend on the commensurator being SL2 of Q?
Not really. No. So you have that they are interalgebraic, So the type is
No, but I'm saying the inner algebricity comes from having the same commensurate.
being commensurable with some subgroup of gamma node.
Okay, yeah, so
Alright.
that's,
Yes.
that's right.
Comes from being
Yeah.
being commensurable with some subgroup.
Yeah.
And that's exactly what the question is.
Yeah.
Are the other non-compact groups somehow commensurable with? And so it turns out that this was looked at, and so all the non-compact arithmetic triangle groups are strongly minimal and geometrically trivial non-compact. So, and the idea is to somehow look into the various types and, as I said, check whether you have what I call modular realization, which means commensurable with some subgroup of PSL2. All right, and so this is somehow by looking at some results of Bayer and Trapezer. Right now, so two of them are well-known type of subgroup of SL2R. So let me perhaps define. So Wn, let Wn be the matrix. Yeah. All right, and so this somehow is what sometimes called Freitag involution. And so consider the group which is generated by all right, so this is a subgroup of SL2Z, SL2R. And it turns out that for the two non-compact case, you can realize one of them for n equals 2 and the other for n equals 3. And so you have that they are commensurable with some subgroup, and this yields interalgebraicity. And then using interalgebraicity, you somehow can with the same argument for SL2, the subgroup, arithmetic subgroup of SL2Z, yield that you get that they are strongly minimal. Now, so the other three out of the 9, somehow it's a little bit more difficult to see. So that was a result of Pedersen, but it appears in the same paper of Bayer and Trapezer. So if you take the free group in free generators, look at the characters defined as follows. Then the kernel is a normal subgroup, and you know besides the generator. Now, take any group with free generators and let the quotient be given by P, right? And look at the character if you want induced from P. And define the kernel to be gamma star. Right? Then somehow a very general result is if you are a triangle group of type 2m infinity, then the kernel of chi star is a triangle group of type m infinity. And so now remember, so these are group of type 2, 4 infinity and 2, 6 infinity, And so somehow you get, by applying chi, a group gamma star that somehow is commensurable with a subgroup of SL2Z. And so you get somehow interalgebraicity in the other compact case. All right? 5 minutes? Right. So, and quickly, maybe. Yeah. So maybe just to, so the covering equations will be determined by, if you look at the modular curve or the compact Riemann surface you get. So and these ones are degree 2 and degree 2 in this case as well. And so this somehow explain the interalgebraicity between the various Hauptmodules for these. Now, so to finish, I want to somehow say a few words about generic triangle function. So, by the way, I should say first that this is the state of this problem. So for all non-compact triangle groups, we know that they are strongly minimal. For compact arithmetic, this is somehow a very difficult problem, but one could, for example, try to do the same thing as the Axel-Demand Weisbach theorem with derivative using a minimality and so on and so forth. And for the rest, it's wide open, right? So trying to understand strong minimality is a wide open problem in these cases. But one thing I've noticed, so there was in a paper in a preprint of Hoodie and Itai, so the first version of the model complete paper. So a talk would be a talk of mine if there's no Penderweg equation. So let's go. So there's a way to obtain P1 from P2. So by specializing the parameter E at 0. All right. So the first Penderweg equation can be given by specializing this P2 at alt E equals 0. So I'm not writing down the equations for E because somehow it's not the usual form of the equation, but there's a very well-known cascade of relation between the various Penderweg equations. And so Penderweg claimed that if you knew that this guy is strongly minimal, then you should be able to use that to figure out that P2 was strongly minimal. And so Udi somehow looked at this argument and tried to do an argument with the order, but it turns out that that somehow doesn't really work. But so if you look again at Udi's proof, you see that you could make this argument work if you had, let's say, a discrete amount of information, infinite discrete amount of information. So let's say you knew for discretely many equations, they're strongly minimal, then you could somehow conclude that the generic values would be strongly minimal. And so one could try these ideas with this family. And what we have, for example, is for infinitely many v's. So I work with this special form of the equation, but there's nothing, it has nothing to do with the idea, but it's easier to rewrite it here. So for infinitely many c's, you have Nishoka's result about what I've written down, that no solution satisfy an ADE of order 2. And now, by modifying the argument there, one actually can show that for generic values of the parameter, the same property will hold for AD over Q of V. All right? How much time? 3 minutes? So, I mean, I don't know if I have time to maybe sketch the proof of that, but let's perhaps look at the idea of how one could do some. So let's say for alpha generic, so V generic, let's call the solution here x of V, so xv, so sum y1 in xv satisfy an order 2 equation. So the idea is to look at the locus, let's call U, the locus over QV, the Cauchy locus of V and Y1. All right? So now this naturally lives in the set X of V, let's call this V1. Set Vy such that dA y equals 1 minus V squared R naught Y, so the total space. And so one looked at the projection of to the constant. So now let's look at the preimage of V1 in according to pi. So and let's call this yes, and that's not what I want to do. So I have the argument. I better just rely on it. All right. Yeah. So now you let. So first of all, know that the order of U is 3. Order of X is 4. And the claim is that pi of U is an infinite definable subset of the constant. All right. So Right, so if you somehow look at the projection of u to the constant, it's an infinite definable subset of C. And the reason is you use the fact that the V1 was a generic point of the constant. So it cannot be in a finite set. And so there must be one of these elements that are in the, so let's call it D2 in C, such that you look at the containing U, and then you look at the actual locus of V2. And so since the order of the locus of V2 will, so let's look at the, let's call U prime. U prime, V2y, such that the equation O. And from there, you can argue that the intersection, which is non-empty, should be the order of U prime plus order of U minus the order of U. Order of X. And so this will give you that the order of the intersection is 2, and so that there must be a solution that satisfies an order 2 equation, and that's where you get the contradiction. All right? And so I'll end here.
Do you have any additional questions?
Yes.
Let's say we are considering the graph of differential equation of order 2.
Yeah.
Is there any relation between differential equation of order 2 cannot be reduced to differential equation for order 1 and strong minimality group?
So strong minimality properties. So you can't have solutions of that satisfy an order 1 equation, right? If you're strongly minimal and you have order 2.
Okay. And given differential equation of order 2, is it possible to compute or to check algorithmically the strong minimality?
What do you mean no? We don't know, right? It's not possible means it's not decidable, we don't know. It seems very difficult.
Yeah.
Okay.
Might be possible.
Yes.
So what's left then for the generic case to show strong, the expectation is generically it will be strong and minimal.
Yes, and
So
so
you need an axial minimum bar stress?
well, so the thing is, so you see for the Schwarz triangle function, they're not really Hauptmoduls, so they won't really have this
Makes sense.
linear exactly. So it's really for non-arithmetic triangle groups that even this question of maybe a form of you should be able to show that it's independent. The various J functions are independent in any case. So I think Jim would like to conjecture that the arithmetic type should be strongly minimal, trivial and Ω-categorical, non-arithmetic one, trivial and strictly disintegrated with stuff. So maybe the last thing, so the way I'm coming at this problem is not to look at the only minimality side of things. I'm really trying to look at it from a differential perspective and try to see if I can get strong minimality, which we know is difficult. But the one avenue is there is a different form in which you can put these equations in a first order, so in a differential, in a d-variety form, where the polynomials involved are very symmetric in a lot of ways. And so this, I think, reduce the amount of subvarieties that you might have for the. So this is somehow the way I'm attacking this.
Other questions?
I just have a comment like on how hard it is to tell strong minimality. I mean, like examples of Ronnie's suggest that it should be pretty hard because, for instance, like your work with Ahmed on these Panel-Day equations, you have strong minimality on, or you have strong minimality in almost everywhere, except for an infinite discrete set of points in the complex numbers. So whatever sort of algorithm you design would have to identify these infinite discrete sets. And the invariant subvarieties in that case, they necessarily grow in degree. It's unbounded. So it's not, it's not uniform. So it seems quite hard. That's my opinion.
Clearly a challenge. Other questions? Let's thank the speaker again. So we'll take a 10-minute break, and we'll start at 11:20 with somebody who was recently associated with us.